In pursuit of transferring technical knowledge and just to gear up the new engineering entrant, myself Pranab is here to deliver today's presentation, Power Transformer Part 76. As the topic is of the continuation, so for your convenience, the link of the previous one is given under the description box. Let's start with factors influencing the ionic mobility at the oil paper interface. From the study, it is to understand that the ionic movement and their transport process would have an important correlation with charge transport in oil paper insulation. It is rather so much significant as because the ionic mobility between oil and paper that leads to the formation of an electric double layer near the oil paper interface. The characteristics of ionic mobility is being directly influenced by the underneath factors. 1. External electric field strength. Number 2. Temperature. Key chemical and physical properties of the existing oil, that is like acidity, water content, sludge accumulation, viscosity, ionic contaminants. Number 4, key properties of the paper, cellulosic paper rather, such as its molecular structure, surface charge, porosity, and ion exchange capacity. Ionic mobility at the oil paper interface is influenced by external electric field. An electric field is being responsible to drive the ions in transformer oil to move in a specific direction. Higher electric fields can enhance the mobility of ions. Difference in ionic mobility between oil and paper that leads to significant accumulation of ions at their interface, causing to create an electric double layer near the oil paper interface. Temperature. Higher be the temperature, that would responsible for increasing the kinetic energy and mobility of the ions in oil. Chemical physical properties of in-service contaminant oil. Surfactants and other ionic impurities in oil can have to affect the respective ionic mobility. It is as because that has to alter the oil's ionic interaction and viscosity. Factors related to cellulose-based paper insulation. Ions mobility would have been dictated by the paper's physical structure, which includes its pore size, intricate pathways within the porous materials, and surface morphology. Surface morphology refers to a qualitative evaluation of the shape, texture, and physical structure of a material's surface, like porosity, roughness, etc. Dynamics of ionic mobility dictated by the oil's specific characteristics. A stronger electric field that has to exert a greater force on the charged ions and does significantly increase the ionic mobility. Number 2, the electrostatic force as generated is directly proportional to the electric field strength. So because of the increased force, that would have to accelerate the movement of ions more rapidly, leading to a higher drip velocity as the electrical force overcomes frictional forces more effectively within the oil. Therefore, drip speed as acquired by the ions per unit applied electric field is directly translated to ionic mobility. Ionic mobility is also significantly influenced by the effective charge and size of the ions. A higher effective charge on an ion would have to occur when ion interacts more strongly with polar molecules of transformer oil. If there is strong interaction between an ion and its surrounding polar molecules in oil medium, then the ion would have been readily trapped by the surrounding polar molecules. It is rather to be understood that the ions are being categorically dissolved in accumulated polar solvent in oil. Due to electrostatic attraction, the polar molecules have met to orient themselves around the ion, forming a solvation cell or solvent cell around the ion. The size and density of the solvation cell are always being directly influenced by the characteristics of both the ion and the polar solvent molecules. So, this organized structure as formed through solvation is quite crucial for the ion's behavior in the solution or mixture of the oil mixture rather. Now, it is to be noted that the term solvent is a state of substance which is being uniformly dissolved within the solvent like insulating fluid such as transformer oil. Solvation is generally referred as the process where solvent, that is oil, where solvent particles that are to surround and interact with dissolved solute particles, leading to their dispersion and stabilization within the solution. These interactions are invariably based on intermolecular forces between the solvent and the solute molecules and are to be much crucial for the solute to dissolve or to disperse. Solute would have been in dissolved state when the solute solvent intermolecular forces that must be strong enough to overcome both the solute and solute, solute and solvent intermolecular attractive forces. Whereas solute would have been in dispersed state when the solute solvent intermolecular forces that must be too weak to overcome both the solute and solvent intermolecular attractive forces. So, solute in dispersing state would have to create a heterogeneous mixture when particles remain as distinct visible units suspended within another substances like colloidal state. However, in paraffinic based transformer oil, where the solute would usually be in dispersed state, as because the solute solvent intermolecular forces are being weaker than the solute and solvent intermolecular attractive forces. In naphthenic based transformer oil, where the solute would usually be in dissolved state, as because the solute solvent interactions that are to be strong enough to overcome both the solute and solvent intermolecular attractive forces. The aggregation or coagulation phenomenon of ion and polar molecules would obviously have to increase the effective size of the solvation cell, causing to enhance the flow resistance as a form of friction, which impedes the ion's movement and thus decreases its mobility. Paraffinic based transformer oil is primarily composed of saturated hydrocarbons which configured with long nonpolar chain of carbon and hydrogen atoms, making the overall hydrocarbon molecules nonpolar and generally be of non-reactive. As the paraffinic based transformer oil is nonpolar, so its inherent characteristics that leads to a low affinity and thus would have limited interaction to charged particles. Paraffinic based transformer oils are being typically exhibited a higher viscosity index compared to naphthenic based transformer oils. Viscosity index that has to quantify how much an oil's viscosity, that is resistance to flow, would have to change with temperature. So, higher be the viscosity index, which thus to indicate that the viscosity of paraffinic based transformer oils would have to remain relatively stable over a wide temperature range than that of the naphthenic based transformer oils. Naphthenic based transformer oils typically have higher density than paraffinic based oils at the same viscosity and temperature. It is because there would have the difference in their chemical structure, where the naphthenic oils, which are being more dense due to their cyclic structure compared to the more linear structure of paraffinic oils. However, viscosity is of two types. One is dynamic viscosity, which represents with mu, and kinematic viscosity, which represents as V. Dynamic viscosity would refer as a measure of the internal resistance of the fluid to motion, and kinematic viscosity is the ratio of dynamic viscosity to density, density of the fluid. তাহলে kinetic viscosity equals to dynamic viscosity divided by density of the fluid. Having with the same viscosity and temperature, naphthenic based transformer oils would typically have a higher density than that of the paraffinic based oils. So, naphthenic based transformer oils must have to possess the lower kinematic velocity, causing to have higher ion mobility than paraffinic based oil. The ion mobility in naphthenic based transformer oil is rather being highly sensitive to temperature changes. Impact of higher temperature on ion mobility in naphthenic based transformer oil. The oil viscosity would have to decrease, allowing ions to move much faster. Kinetic energy and movement of the oil molecules would have been enhanced. Increased molecular motion can help to dislodge and thus to facilitate the movement of charge ions, that is, charge carriers rather. As the ion mobility increases, that directly leads to increased electrical conductivity of the oil. Excessive temperature rise that would have to create much more charge carriers in oil, causing to have further increase of oil's conductivity and dielectric loss. As of the consequence of increasing ion mobility and the overall movement of charge carriers, that can further help to enhance both polarization and DC conductivity within the paper insulation system. Solid insulation as being composed of cellulose based paper, so with rise of temperature, more water would have to migrate from the cellulosic paper into the insulating oil by the process of increasing molecular thermal motion. These water molecules, as mixed with the oil, that can significantly reducing oil's dielectric strength and increasing its conductivity. Impact of oil absorption. Impact of oil absorption rate on ion mobility in naphthenic based transformer oil. 1. Higher ion mobility is one of the most intrinsic property of intrinsic property of naphthenic based transformer oil, as the ions within oil would have to move more easily and are being to attain a greater speed under an applied electric field. Oil absorption rate is always be crucial, as because this has to dictate the actual trend of how much oil is to be absorbed by the solid insulation like the paper and pressboard in a transformer, and how that oil would have to interact with that solid insulator. Number 3, higher be the oil absorption rate, that has to indicate the mobile ions within oil would have been more readily transported across the insulating system. Number 4, however, changes in temperature that has to influence the fluidity behavior of the oil due to variation of molecular motion of ionic dissociation, creating to alter the mobility of ions. Phenomenon of an increased rate of ion mobility that would cause to accelerate the magnitude as well as the speed characteristics of charge accumulation at the interface of oil and paper insulation. Layout of the trap charges at the oil paper interface is another to be influenced by is rather to be influenced by the factors including 1. Inherent difference in conductivity between oil and paper insulation is primarily responsible for charge accumulation at the oil paper interface. Number 2, difference in molecular structure and electron affinity of the oil and cellulosic based paper would have an impact on the distribution of charges in the electrochemical double layer as formed at the oil paper interface. Electrochemical double layer would thus to act as a charge barrier, causing to hinder the charge transportation process, causing excess charges to accumulate. Other influencing factors that are also to include as hereunder. A. The chemical composition and conductivity of the insulating oil. Higher be the moisture content in the insulation material, that has further to promote greater amount of ion dissociation and conductivity. Number C, it is as because there would have the every possibility of water molecules to ionize under applied electric field. D, this has to introduce more mobile ions and thus to create additional charge carriers within the insulation material, causing to increase its electrical conductivity. The combination of increased charge injection and greater mobility leads to a greater accumulation of trapped charges within the insulation, forming space charge distribution. These space charges can accumulate at the oil paper interface as due to have the conductivity difference between oil and cellulosic paper, leading to charge trapping at their interface. Impact of space charges to accumulate at the oil paper interface in transformer insulation. The space charge accumulation that has to build up at the oil paper interface as because due to significant differences in conductivity and permittivity between the oil and paper. Number two, the paper as it acts as a barrier causing to restrict the charge movement in oil paper insulation, and that has to create an electric double layer at the oil paper interface. Formation of electric double layer is rather to be a potential energy barrier that has to occur due to the basic difference in electron affinity between cellulosic part of the paper and the oil, causing negative charges to accumulate at the surface, and positive charges would have to diffuse into the oil. An increased rate of charge injection combined with a high charge mobility that would allow to accumulate a greater number of charges deep within the insulation. Mainly in solid insulations, there would have the natural tendency to accumulate trapped electrical charges within their molecular structure. Number 6, thus any sort of electrical charges as introduced by an external electric field thus any sort of electrical charges as introduced by an external electric field can have become trapped the charge carriers within the material's molecular structure instead of immediately dissipating. Most important, any sort of electrical charges as introduced by an external electric field can have become trapped the charge carriers within the material's molecular structure instead of immediately dissipating. Such phenomenon is known as space charge accumulation, and that has to create a greater influence on the distortion of electric field distribution, especially at the dielectric interfaces like oil and paper. Key factors that are not supporting to use naphthenic based oil in transformer. At the operating stage, naphthenic oil would have to undergo more significant changes in its electrical properties due to these underneath factors potentially leading to faster deterioration of the transformer insulation system. 1. Ion formation as it is being created more readily under any sort of electrical stress. In case of naphthenic based transformer oil, a flow of charge carriers would have been constituted when the ions that are to move through the oil under the influence of an electric field as it exerts a force on the charged ions, causing them to migrate through the oil, thereby generating an electric current. Naphthenic based transformer oils must have to possess the lower kinematic velocity, causing to have higher charge mobility than paraffinic based oil. Higher charge injection is mainly due to the higher movement of charge carriers across the insulation interface. Naphthenic based transformer oil is much more sensitive to temperature as because its viscosity would have to decrease with the rise of temperature, which in turn has to influence the increase of ion mobility within the oil, causing to increase the electrical conductivity of the oil itself. Paraffinic based transformer oils, as are being lower density than naphthenic based oils at the specified temperatures, So, their molecules have to possess higher kinematic viscosity, causing to exhibit lower ion mobility. However, naphthenic based transformer oils with higher densities and to contain significantly less amount of paraffin hydrocarbon, that is wax, would have to offer superior low temperature properties such as a lower pour point compared to paraffinic oils, which have higher pour points due to their higher wax content. Lower wax content of naphthenic based transformer oil that has to keep ensuring its fluidity, characteristics, and insulation properties, even in the case of an extreme climate with temperatures as low as minus 40 degrees centigrade. Paraffinic based transformer oils are comprised mainly of alkanes and have to contain long straight chains or branched hydrocarbons. Such type of structure that has the paraffinic based transformer oil to allow higher stability of higher stability at high temperatures and lower volatility, making them more suitable for high temperature applications. Whereas naphthenic based transformer oils are comprised of cycloalkanes and have to contain a ring like structure which offers less stable at high temperatures. As the straight chain hydrocarbons would have to resist breaking down at high temperatures, so paraffinic based transformer oils would thus to offer higher oxidative stability than that of the naphthenic based transformer oils. Naphthenic based transformer oils generally exhibit a lower viscosity index compared to paraffinic based transformer oils. A high viscosity index means the oil's thickness changes very little with temperature, which thus leads to stable performance in both hot and cold environment. A low viscosity index naphthenic based transformer oil that signifies a greater change in the oil's viscosity with temperature fluctuations, which thus tends to provide better performance only at the lower temperatures because the oil indeed has to offer better low temperature fluidity. So, paraffinic based transformer oils are commonly used in transformer applications where the temperature stability as well as oxidative stability both would have been the prime requirement for their required optimum performance. Therefore, the basic difference in paraffinic and naphthenic oils that are to be often characterized through their chemical structure, physical properties, and the purpose where to use, that is environmental situation you have to consider. Key difference between paraffinic and naphthenic oils. Properties, chemical structure, properties, paraffin oils and naphthalene oils. Chemical structure, straight chain and branched chain alkanes in case of paraffin oils, cycloalkanes, ring structured hydrocarbons in naphthenic oils. Viscosity index, higher viscosity index indicating viscosity changes less with temperature in case of paraffinic oils. For naphthenic oils, lower viscosity index indicating greater viscosity changes with temperature. Pour point and presence of paraffinic hydrocarbon. Higher proportion of paraffin hydrocarbons resulting in a higher pour point, more prone to solidify at low temperature. Lower proportion of paraffin hydrocarbons in case of naphthenic oils resulting in a lower pour point would have to maintain fluid at lower temperature. Annealing point. Annealing point. Annealing point high in case of paraffinic oils, typically around 93.3 degrees centigrade to 126.7 degrees centigrade. Whereas in case of naphthenic oils, low annealing point typically around 65.6 degrees centigrade to 76.7 degrees centigrade. Aromatic content, low aromatic content in case of paraffinic oils, whereas naphthenic oils, higher proportion of naphthenic and aromatic molecules. Oxidation resistance, higher resistance to oxidation and stable at high temperatures, whereas naphthenic oils, lower oxidation resistance but better solvency power. Stability, in case of paraffinic oils, more stable at high temperatures, less prone to breakdown. Whereas naphthenic oils, less stable at high temperatures, dissolves substances better. Thermal conductivity, comparatively higher in case of paraffinic oil, and for which it is efficient for maintaining optimal operating temperature and ensuring transformers longevity. But in case of naphthenic oils, comparatively lower thermal conductivity, and that has to offer better low temperature performance and lower viscosity. Electrical properties. Under anhydrous conditions, the breakdown voltages and dielectric losses of paraffinic based and naphthenic based oils are almost identical. Now, the conclusive part is that 1. The key physical properties of mineral transformer oil should have to be high flash point, low viscosity for efficient cooling, low pour point for cold weather operation, high dielectric strength for insulation, and low moisture content to prevent degradation. Number 2, other important properties that would have to be of high resistivity, high thermal conductivity, and good oxidation stability. These two are the considerable points for making suitability of the transformer oil. Properties based on IS 335 Indian standard. Mineral transformer oil. Density at 60 degree Fahrenheit or 15.6 degrees centigrade, 0.880 gram per centimeter cube. Kinematic viscosity at 68 degree Fahrenheit at or 20 degrees centigrade, 22 CST. Kinematic viscosity at 212 degree Fahrenheit, that is 100 degrees centigrade, 2.6 CST. Fire point 338 degree Fahrenheit, 170 degree centigrade. Pour point minus 58 degree Fahrenheit, minus 50 degree centigrade. Flash point 320 degree Fahrenheit, 160 degree centigrade. Auto ignition point 536 degree Fahrenheit or 280 degree centigrade. Specific heat capacity 1860 joules kg Kelvin, joules per kilogram per Kelvin. Thermal conductivity at 68 degree Fahrenheit, 20 degree centigrade, 0.126 watt per meter Kelvin. Thermal expansion at 68 degree Fahrenheit at 20 degrees centigrade, 7.5 into 10 to the power minus 4 degree centigrade degree per centigrade. That is, oil volume increases by the value 7.5 into 10 to the power minus 4 times its original volume for every 1 degree centigrade temperature rise. Dielectric dissipation factor at 194 degree Fahrenheit, that is 90 degrees centigrade, maximum 0.002. Permittivity at 68 degree Fahrenheit, that is 20 degrees centigrade, 2.2. Specific resistance, that is resistivity at 90 degrees centigrade, 35 into 10 to the power 12 ohm centimeter minimum. Specific resistance, that is resistivity at 27 degrees centigrade, 1500 into 10 to the power 12 ohm centimeter minimum. Oxidation stability, neutralization value after oxidation 0.4 milligram potassium hydroxide KOH per gram of oil maximum. Total acidity. Neutralization value for new transformer oil 0.03 milligram potassium hydroxide KOH per gram of oil maximum. Let's stop here. Further to be continued at later stage. Thank you. Thank you for listening the video. Kindly do like, share and subscribe. Your subscriptions would encourage to post more videos. Also share your comments or feedbacks inside the dedicated comment section. If you have any suggestions or specific topic you want, then let me know in the comment section, please. Thank you.